slower. Speaking of slower, I'm aware that I talk way too fast. I got kind of an auctioneer / rapper thing going sometimes. I'm pretty thick-skinned about the whole thing. Obviously, if you are thinking that I'm going too fast, you are always welcome to tell me to slow down. I am very, very aware that I'm going too fast. This Black Mirror has been looking for an app for me for years that was like recording, and then when I'm going too fast, would, I don't know, vibrate or something like that, so I don't go too fast. So anyway, always let me know. So today we're going to talk about a couple of topics, just kind of wrapping up the end of the forces within these plate tectonics type forces. And then we're going to go forward and talk about earthquakes. And so we're going to talk about, let's see, we're going to finish this up here. Where we go here? Present with there. Just going to kind of finish up the last few slides about this section here. We've been talking for a couple days now about plate tectonics, about the different plates on the Earth's surface and the lithosphere and how they're moving. And we've never actually talked about how we know that. What is the actual set of, what is the evidence we have that the plates are actually moving? I mean, I know that the North American plate is headed off to the west and the European Eurasian plate is headed off to the east. And we keep throwing around this number that they're moving about as fast as fingernails grow. But it isn't like we just sort of have a tape measure out there measuring it. How do we actually know things like the plates are moving? And one of our best pieces of evidence about this is what's called paleomagnetism. Paleomagnetism. The word paleo always means old or fossil or something like that. We all know that the Earth has a magnetic field. The Earth is basically a big bar magnet. It's a little complicated as to why, and it's not even entirely well understood by scientists, but we know that the Earth is a big magnetic field. That's why compasses work the way they do. If we had a compass here in the room, and I meant to bring one today and forgot, but we would have all gathered around it anyway, we know that because of the Earth's magnetic field, the compass needle would point to the north. Compass needles aren't the only thing that does that. There are minerals that form when they crystallize out of lava, out of magma. They orient themselves so that the crystals point north. We'll learn in a moment or two about the mineral magnetite in particular does this. And so when we look at a rock that contains magnetite, we're effectively seeing kind of like a fossil of what the magnetic field used to be. When magnetite is in magma and is a liquid, it's not magnetic. But as it cools down and starts forming crystals, the crystals line themselves up to point towards the north magnetic pole. So when the rock cools, we now know it was pointing, north was that way. Well, the north magnetic pole was that way. It's like a frozen record of what the Earth's magnetic field was like at that time. Now, if that rock gets moved around and stuff like that, that could mess all that up. We don't know. But if the rock was, say, just formed as part of seafloor spreading, the seafloor is spreading out, the North American plate's heading off that way, the Eurasian plate's heading off that way, and magma is just welling up in between, cooling off. As that magma cools, it tells us which way Earth's magnetic field was. Now, there's a lot of weird things about the Earth's magnetic field, but one of the really weird ones about it is the Earth's magnetic field flips every now and then. Every few 100,000 years, again for reasons that are not well understood, the Earth's magnetic field flips. This doesn't just happen any old day. I mean, it takes like thousands of years for the flip to happen. But right now, if you have a compass, it points to the north. But 100,000 years from now or something like that, it might point that way. South. And this is actually a well-known phenomenon in science, and we can use it to do all kinds of things. But in particular, we can use it to see seafloor spreading. Here's some seafloor spreading happening along a mid-ocean ridge. This is the freshest rock right here at the beginning where magma has welled up and cooled. And all of that fresh magma has magnetite crystals in it. They're all pointing to the north. And new seafloor is welling up in between, pushing this out all the time. So like these rocks are a little bit older. But those rocks, let's say that was 250,000 years ago, those rocks cooled when the Earth's magnetic field was the other way. And all their magnetite crystals are pointing to the south. And if we go a little farther out, we'll hit a strip where the magnetite is again pointing to the north, because that was the direction when those rocks formed, the magnetic field was. The newest rocks are right here, and we get these stripes of places where the magnetite crystals are oriented to the south and places where they're oriented to the north. And this is actually something that is pretty easy to observe. There's specialized equipment that can be pulled behind a boat or pulled behind a submarine or whatever. They can measure on the seafloor which way the magnetite crystals are oriented. And you get these kind of maps that show, like, for example, off the west coast of the United States, here's Seattle and Oregon and so on. Here's the mid-ocean ridge for the Juan de Fuca plate. This is the newest rocks. All its crystals point north. Right next to it, there's an area of crystals pointing south, then an area of crystals pointing north, and you get these alternating bands. I had no idea that those bands are called isochrons until I got that question wrong on that stupid test yesterday. I had to go look it up afterward. Those bands are called isochrons, which in retrospect makes kind of sense. Iso means equal and chron means time. Isochron is a Greek word that means formed at the same time. But they show us how the seafloor was spreading. So if we know that, like, the Earth's magnetic field reversed to us to the north at this point 4 million years ago, and this is 40 miles away, we know that it moved 40 miles in 4 million years. And we can do the math and figure out what the rate of seafloor spreading is. This sort of paleomagnetism data is one of our best ways of being able to prove that this kind of continental drift is happening. It gives us concrete evidence, without us actually being out there with a tape measure, of how the seafloor is spreading and how fast it happens. And it's pretty fast, I mean, compared to the age of the Earth. The rocks that form here on this mid-ocean ridge rather, on the Juan de Fuca plate, you know, by maybe a few tens of millions of years, will already be all the way over here by the North American plate and start subducting under the North American plate. This is why we talked about right away the first day of this module about how rocks on the seafloor just aren't that old. They're constantly being produced in the mid-ocean ridges, and they're constantly being destroyed as they go down and get subducted into the Earth's mantle again. Now that tells us why. Why are these plates moving? It shows us that we have an observation that they do, but it isn't necessarily telling us why they do. My kids are addicted to shows like Magic School Bus and Sid the Science Kid and crap like that. Excellent. Better than they could be watching SpongeBob. I mean, yeah, whatever. And I know on those shows they usually say it's about the flow of the molten rock under the continents. We could use a fancier word than that. The right word is convection, where like the magma underneath the continental plates is moving. Convection means like warmer parts are rising and cooler parts are sinking. But just in general, the flow of the magma under the plates. And that's a really good picture to have in your mind, that as this magma flows, it sort of drags the continental plates with it. And it's a lovely idea, but it isn't actually a very big part of the story. Magma does move underneath the continental plates, but it isn't very good at making the continental plates move with it for a number of reasons that are beyond what we're going with here. This is not really the main part of the story as to why plates move. A much bigger part is what we've talked about a couple times so far this semester, this idea of slab pull. This is the heavy blanket idea that we had. Remember the heavy weighted blankets? If you think about a plate of oceanic crust as being one of those weighted blankets, look over here on top of the magma. As it starts getting pulled under, as it has a convergent boundary with continental crust, and it starts getting pulled under, just like the heavy blanket, its own weight starts pulling it off the table. As this plate off the ocean crust, it starts getting pulled down, but pushed under this this continental. Its own weight is pulling it off, just like the heavy blanket pulling its way off the bed or off the table or whatever. That's called slab pull. And that's actually the biggest reason why the ocean plates are going the way they are. Once they start pulling, once the leading edge of this plate is forced down under the continental plate or wherever, and its own weight is then pulling it down into the crust, into the mantle, and just drags the rest of the ocean crust with it. With techniques like seismic imaging and things like that, we can actually see that old ocean crust, now a couple 100 miles down deep in the mantle, melting and being recycled into new mantle. This is the main process that's going on. Another process that's going on is something that we talked about briefly. I can't remember if it was this section or the morning section. I said these places where the plates are being pulled apart and fresh magma is pushing its way in, that space in between, does that also push the plates apart? Sure, that's called ridge push. So like if this area right through here is the Mid-Atlantic Ridge, over that way is North America, over that way is Europe. As these plates are pulling apart and new magma is welding in between them, forming new rock, is that pushing the continents apart? A little. That's part of the story too. So there's three processes going on, but slab pull is by far the biggest as to why the plates are moving the way they are. So for the land masses, like North America, the main story is they're just being moved around by the oceans around them. As the ocean plates do things like grow by ridge push or get dragged down by their own weight through slab pull, they're just pushing the continents around with them. There's no magic here. It's just the continents are getting pushed around as the oceans move around. Well, the ocean crust moves around. There's no other magic there. It's just sort of how it's going. And that actually ends chapter 4 of the book. Chapter 4 is the one that talks about all of these processes of plate tectonics. How and why things move in the Earth's crust. Why do plates form? Why do they move, etc. The rest of this module is about what that means. Things like earthquakes and volcanoes and mountain building. So let's go forward. Remembering that we want to have a slightly easier Friday. It's a Friday. And I'm in a forgiving kind of mood because, like I said, I just had to survive a day of 125 question test that was no fun whatsoever. I made so many stupid mistakes. That's what happens. So let's talk about earthquakes. And I don't feel like I'm in a mood right now to like actually pick through and be like, look at all these words EDSC sent me. They're the kinds of things they want you to know on the test. We'll get to all these things in chapter 5 of different words. Some of them we get to today, some of them we get to other days, some key concepts, blah, blah, blah. Probably more broadly than like a big list of vocabulary words, is that you want you to be able to describe the mechanism that generates earthquakes. Sketch it, think a little bit. I don't know exactly how to bring that. But to be able to describe the mechanism that makes earthquakes. That's not a small question. I mean, folks have wanted to understand earthquakes for thousands of years. And they've had ideas about that, mostly bad ideas. Avery, earthquakes are caused by an angry God because of your sins. Sorry, it's your fault. No. Well, obviously ideas like that were around for a long time. But in the more modern era, like we just talked the last few hundred years, there was an idea that seemed kind of reasonable, and that earthquakes were just caused by the fact that the Earth is getting cooler. Then the whole big, well, not like the, not global warming thing, I mean like the whole big fall of rock, a molten rock that is the Earth, is getting cooler with time, and so it's probably shrinking, and as it shrinks, it kind of shakes as it gets shrinking, and that seemed kind of reasonable. It's not even a little bit true, but it seemed kind of reasonable. It was a perfectly good explanation for a long time, and it took a long time for us to get a better idea. I mean, if you just experience an earthquake, there isn't much of a clue in what you experience as to what actually happened. What caused the earthquake? And an earthquake is the ground shaking caused by the rapid movement of a block of rock slipping past another along a fault. I can assure you, if you're experiencing an earthquake, what you basically know is it shook a lot. And it turns out the shaking doesn't really help you understand what happened. It's this idea of big blocks of rock slipping past each other along faults. And it's going to take science a long time to understand what they meant by this idea of faults and what the earthquakes were doing along the faults and so on. I mean, we've looked at pictures like Google Earth images and aircraft pictures that showed faults before and how they were sort of like the boundary between plates. In general, there's sort of a crack in a plate. I mean, I can picture the San Andreas Fault. Remember, we saw that the other day. One side of the fault, it's North American plate. The other side of the fault, it's Pacific plate. And they're trying to move in separate directions. But they actually kind of get stuck on each other. The word for that stuck is locked. They get locked. They don't just slide past each other a couple inches a year. They get stuck for maybe a couple decades as forces build up, and then finally they break and they get unlocked and they slide a couple feet in maybe a minute or so. They get stuck, they get locked. This idea of locked is kind of a difficult picture to understand. They get locked because of the weight of all the rock. We looked at pictures of faults. They were at the surface. But that fault is a crack that extends all the way down to the lithosphere, maybe 40 miles. Up at the surface, it's kind of easy to see what's going on. But down deeper, the two sides of the fault are really squished together just because of the weight of all that rock above us. The weight of all that rock above us is a term for what did it say there? Confining pressure. Confining pressure was a term on the last test. That was the weight of all that rock above you. One of the teacher's guides for this lecture suggests, this was obviously before the era of COVID, that we do a little example of how confining pressure can lock boundaries together. And what it says is like have the students all sit on like a bleacher or something like that, side by side. I mean cheek to cheek here. Like one person's right here and the other person's right up there butted up against them. And you got them all in there, they're really tight. Okay, now get the middle person to move out. Well, they're kind of stuck, right? The pressure on them on their sides and stuff, they're kind of wedged in it. Frankly, that sounds like a horrible thing to do, COVID or not. I don't think I really want the students all wedged in there like that. But you can picture the idea, right? You're just wedged in there so tight. Your own weight is kind of squeezing each other's cheeks together, okay? There's just no room. In the same way, the weight of all those miles and miles of rock on top of it has squeezed that fault so tightly together. It's locked. But at some point, the forces will build up enough that it'll break. That doesn't in general happen up at the surface. It generally will happen someplace deep along the fault. And that place where the rock finally breaks and we can start sliding, that's called the hypocenter. The hypocenter is the place where the breaking started. It's in general not at the surface. That's not a word you've probably heard before, hypocenter. Because generally speaking, people talk about the epicenter. Let me see if I've got that. I think I have a slide here that says that. Yeah. The hypocenter is where the actual breaking happened, and it's typically some miles below the ground. The epicenter is the place on the surface directly above it. I mean, when you hear about an earthquake, And it happened in Northridge, California. They don't really mean the place that the rock broke was in Northridge. It was below ground there. Northridge is just what's directly above it, the surface. So the epicenter, which is the term we tend to use to describe it, it's just because that's where it is at the surface. When that rock breaks, there's just enormous amounts of energy stored, as these plates have been trying to grind their way past each other for maybe 40, 50 years. They've been storing up energy, just trying and trying, and when they finally break, there's just huge amounts of energy. And that huge amounts of energy ripples away from the place where the rocks broke in the form of seismic waves. These will be waves of shaking in the rocks. We will, on Tuesday, learn a lot about the shaking of the rocks and how these move as waves and all that good stuff. But that's obviously what's causing the damage from an earthquake, is these big rippling motions in the rock. You don't normally think of rock as moving, much less rippling. This is a big motion of the rock. We don't have a lot of earthquakes here. We have some. There was an earthquake in Evansville about, okay, first off, there's been earthquakes. If you go to the Indiana Geologic Survey's website, there's a couple earthquakes a year in the area, but they're generally too weak to be felt by humans. But there was an earthquake that people felt about 4 or 5 years ago. Do you guys remember that? I don't really remember very clearly. That was very shortly after I moved to Indiana, and I was actually in the shower when it happened. I have to admit, I just thought I had slipped a little bit. I hadn't realized that things had moved. And then I got out of the shower, my wife was like, "Did you feel the earthquake?" Oh, well, no, I didn't know. So that was about 4 or 5 years ago. There was one. There was an earthquake in Evansville before that in about 2006 or something like that. I'm not exactly sure. You guys would have been pretty little. It happened. My wife was here in Evansville visiting her family here when it happened, and then she called me. She's like, "There was an earthquake here," and that one was actually big enough to cause some damage. Nothing huge. A few like chimneys tipped over on houses and things like that. I don't think anybody was hurt or anything. But earthquakes are not at any means rare. I mean, there's websites you can go to that show you all the earthquakes that happened in some window of time. This happens to be like 2 weeks prior to whatever day I got this. Let's see, this was in 2019. I got this particular image. This is all the earthquakes measured around the world in a 2-week period. And there's just zillions of these little tiny dots, especially along the mid-ocean ridges, that are just really weak earthquakes associated with that before spreading. Those don't really hurt anything. They're far from people. They're not that big of a deal. But you can see that even in a 2-week period, there's a fair number of pretty big earthquakes. We don't know yet about magnitudes of earthquakes, like that's a magnitude 6 or that was a 7 on the Richter scale kind of thing. We'll get there, probably on Tuesday. But for now, you'd be forgiven for saying, "Dang, that's a lot of earthquakes for a 2-week period." Because there's so much going on this chart, I'd point out, you might not have seen it, but one of the big clusters of earthquakes is actually right here in Oklahoma. Because when you think natural disasters in Oklahoma, earthquake is what first comes to your mind. Is your master's grade? Do you have another one? All right, so after class, go with me. We have some spares. All right. In the meantime, I don't know. Just hold it to your ears. Like, I don't know. Yeah, Oklahoma actually is one of the main centers of earthquakes right now in the United States. These earthquakes are not being caused by like the kind of like continental plates moving past each other. They're being caused by mankind by fracking. Fracking involves, it's a way of getting natural gas and oil out of the ground by pumping a bunch of water into a deep well, into an oil well, and the water is at high pressure and it cracks the rocks to get more oil and natural gas out. But it also seeps into little faults in the ground and causes little earthquakes. So those are all man-made out there not deliberately, they just happened in Oklahoma. There weren't that many this particular 2-week period, but usually you see a ton right there around Yellowstone. Earlier this week, there was a day that they had over 1,000 small earthquakes in Yellowstone. We'll talk about Yellowstone on a different day, but in case you didn't know, Yellowstone's going to kill us all. It's a giant super volcano. Have you seen that movie 2012? Who's that? John Cusack? I don't know. It's not a good movie at all. But it's a standard computer animated disaster movie in which Yellowstone kills us all. So at least it had that right. It took a really long time for scientists to understand what was going on with earthquakes because they were so focused on the shaking that they were missing what was actually causing it. Boy, scientists wanted to explain the shaking so much, and they were missing things like what we see here. This is a historic picture. It's about 120 years old of an orange grove, I believe, in California. And the trees were planted in nice straight rows, and then whoop, nice straight row, whoops. After an earthquake, so this is like the Pacific side of the plate, and this is the North America side, and in an earthquake, the plate had jumped a few feet. And so from an aircraft, we could actually see it like shifted the rows of the trees. Nobody had noticed those kinds of details and realized that that was what was fundamentally telling us what had happened in the earthquake, is that plates had moved. Everybody was so focused by it knocked the church tower over, which is important too, to not have noticed things like this. Or like here, another historic picture from the 1902 or whatever earthquake in San Francisco. This fence cuts right across the fault. And when the earthquake struck, this side of the plate moved a few feet that way. This side of the plate moved a few feet that way. And now the fence has this gap in it. It was seen as a novelty at the time, but nobody realized that's telling us what actually happened. Here's a crack in the ground that formed in that earthquake. This should have told us the shaking is an effect. It's not the cause. It's not the main thing that's happening. It's the moving of these plates that's happening. But we didn't really understand that at all until the big earthquake in San Francisco in the early 1900s. I want to say 1902, 1901, something like that. I can't remember. It isn't very often that a whole major United States city basically is destroyed. But nothing in San Francisco at that time was built to withstand earthquakes. We didn't really understand what to expect or how to build. That was right about the time that all those buildings had gotten set up for natural gas, for heating and hot water, and actually that time they even used it for lighting. All those natural gas line pipes burst, releasing natural gas. The fires destroyed what the earthquake did. Huge, huge human catastrophe in California in the early 1900s. And that is what finally made scientists really investigate what the heck was going on and start understanding that it's about the shifting of these plates. The shaking afterward is just an effect. We need to have two plates going past each other, and they're locked. And I like what the book does here, illustrate. I just scanned this out of the book. I like what the book does here, where it uses this stick to kind of illustrate what's going on. When the two plates are, say, they're locked together, it's kind of like you got that stick. But as they try to move but are locked, it's like you're bending the stick. There's a lot of energy there stored in the fact the stick is bent. There's a lot of energy stored in the fact those two plates are stuck and they're trying to get past each other. And just like the stick at some point will break and then vibrate, the rocks will eventually break for any number of reasons. And the shaking is what just carries the energy away. And the plate will come to a new position a few feet from where it was before. But this was a huge, astonishing thing at the time. Nobody had thought this through as to what this could mean and how that results in the shaking and so on. Which is kind of amazing considering many of the world's great cities are positioned right where earthquakes happen. This is Tokyo. Overall, I see lots of things possibly going wrong here, not the least of which being that giant stratovolcano in the distance. But we'll talk about Mount Fuji a different day. But Japan has lots of earthquakes. Maybe you remember, I think it was 2010, when there was the giant earthquake in Japan. Like 20,000 people died. Not to mention there was a tsunami. Tsunamis are the waves in the ocean created by the earthquake. Not to mention Fukushima nuclear power plant It was destroyed and ended up being one of the biggest nuclear disasters in world history. We could talk about Fukushima sometime. Every stupid thing they could have possibly done, they did at Fukushima. And then when an earthquake happened, they wondered. Well, that's okay. We do every stupid thing at every nuclear power plant, it seems. We always make stupid mistakes building them. But we have a lot of places where we build, and not only where there's earthquakes, but frankly where there's giant earthquakes. And when you have a giant earthquake, you're going to have aftershocks. These are a series of small earthquakes that happen as the fault kind of comes back to a rest after a big earthquake. You know, the moment of the big earthquake, the fault slips and maybe moves 10 feet. But that would be the place it came to a rest right then is maybe its best. But over the course of the next few months, it might back up a little bit or move a little bit forward, lurch a little bit forward, just before it comes to kind of a rest. Most big earthquakes have lots of aftershocks after, often hundreds. It scares the crap out of the people who've just been through a big earthquake. I mean, if you've been in a big earthquake, let's think of a big earthquake. January of 2010, there was a big earthquake at Port-au-Prince, Haiti. A very unfortunately poor part of the city was completely destroyed by a large earthquake. Well, not completely destroyed. There were buildings that were just heavily damaged. But then, over the course of the next few weeks, there kept being these aftershocks. And well, as there are always smaller, weaker earthquakes than the original, the buildings are mostly damaged now. I mean, you might be able to kind of make do with 3 walls for a while. But the house is not going to do so great when another earthquake comes along, right? So all of a sudden, there's all these aftershocks where people are being killed by relatively small earthquakes as what's left of the house falls in on them. Which is why actually after an earthquake, people usually are scared to death to even go back inside. And usually for a while, like we'll sleep in tent cities and stuff like that to stay away from buildings until they're all clear. We'll talk more about that Haiti earthquake a different day. It's a real heartbreaker. The book does something frustrating here. It wants to tell you about what kind of faults have the biggest earthquakes. Then it proceeds to basically tell you all the faults have big earthquakes. It annoys me. But just to kind of walk through it a little bit, we can have big earthquakes on either the kinds of boundaries where plates are coming together, the convergent boundaries, or the plates where the boundaries where they're going past each other, the transform boundaries. And then it proceeds to tell you, so basically earthquakes happen on both of them. And I don't know that I would get too bogged down. I feel like if I'm going to let you off the hook for some things on a Friday, after I had to take that damn test, I'm feeling like we could probably get off the hook and be like, we don't need to necessarily know, the ones that are on the continent where we have the 2 continental plates come together, that's called a suture fault. Those are thrust faults, and there's mega thrust faults, and they're just terms. I don't know that I would get all that bogged down. That doesn't feel like something that I'm going to let happen on the test. On the transform boundaries, I'd be a little bit more worried about it because the transform boundaries are places like in California, where the plates are sliding past each other. That particular one in California is an example of something called the strike-slip fault. I just popped that in there because it made me mad. I got strike-slip fault wrong on the test list today. Apparently, that kind of type of test fault is called like a strike-slip fault. The fault is just trying to slide past each other. And there's some big stuff here. Los Angeles, San Diego, San Francisco. There's some big cities here, right where this boundary is happening. And this is supposed to be animated, but for some reason it isn't. It's a type of strike, slip, or transform fault. No. California is headed off towards Alaska. 50 million years from now, it'll be up by Alaska. In the meantime, though, it's got to have some movement. Now, Let's think about earthquakes in California. Let's see. We know there was a big one in the year 1900 or 1901 or something like that in San Francisco. In 1989, there was a giant one in the LA area. It was somewhat famous, in part because it was just a big earthquake in a city. But there were double-decker highways. You know what a double-decker highway is, where there's like multiple levels to the bridge, and they can get more traffic that way through there. Several double-decker highways collapsed. And so the people in the second lower layers got crushed by the weight of the bridge coming down from above. There were a lot of fatalities and stuff like that there. But in 1989, goodness gracious, about 30-some years ago already. And there have been some earthquakes in California since then. There were a few some earthquakes in California about 6 months ago or so. But not really any big ones. People have lived in California for thousands of years, like Native American groups. And Europeans have lived in California for over 500 years. Europeans generally are pretty good at keeping records of things like earthquakes, so they have writing and things like that. We know a lot about the earthquakes that have happened in California in the last 500 years, at least when they happened. And we know something important from that. If it's been at least 30 years since there's been a big earthquake in the LA area, and actually most of this place hasn't had a big earthquake in like 100 and some odd years since the big one in California, in San Francisco, that is really unusual. In general, there are big earthquakes along that fault more often than that. Does that mean plates aren't trying to move? No, they're still trying to move. They're just stuck. They're stuck really bad right now. What do you think that means coming? The worstest earthquake ever. No, not necessarily the worst ever, but a giant one. Right? These plates are really, really stuck. And for anywhere from 40 to 120 years, all these places have been stuck. I mean, there have been little earthquakes along it, but no big place of moving. These earthquakes, yeah, go ahead. There was even a fault, or yeah, well, the Wabash Valley fault system is kind of like just east of the state, just west of the state line, mostly on the Illinois side. We'll talk actually about Indiana and earthquakes just a little bit. Okay. Yeah, that's a great question. Yeah, it is really unusual for theirs to have gone 40, 50, up to 120 years without a really big earthquake. There's just huge amount of pressure built up between the Pacific plate and the North American plate right now. When it decides to go, it's going to be a bad one. Have you heard of the big one? It's going to be the big one. Capital T, capital B, capital O, the big one. Because there's just so much pressure built up along there now. So much stress. I feel like we need that in 2020. Right? Doesn't it seem like a very 2020 thing? Like somewhere around December, we need a big earthquake in California or something. Right after a pandemic, near war with Iran, all the things our country's been through in the last few months, an election that'll undoubtedly go incredibly smoothly, we need to round the year out with a giant earthquake in California. So maybe it'll be this year. But it might not be. It might be sometime in the next 20 years, but it's a really good bet. This isn't an abstract thing in the near, like distant future. Certainly in your lifetime, probably, in the next 20 years or something, there will be a very large earthquake in California as they have slipping along the San Andreas Fault. Look where we are here on time. Okay. Now, what about the fault in here? Well, it's not a strike slip type fault, a transform type fault. It's just sort of a weak place in the crust where the crust was trying to pull apart. It was drifting, if you remember that word, a billion years ago. But it still can move a little bit. And in fact, from time to time, it moves a lot. We talked before about, was it in the 1800s sometime, the New Madrid earthquake, which happened up part of the Wabash Fault. One of the biggest earthquakes in U.S. history. But we can understand that fault fairly well. We know that those are fairly far apart. Big earthquakes along the Wabash Fault are hundreds, if not thousands of years apart. There is some chance there will be an earthquake in Evansville. We don't yet know how to do this business of ranking their size, their magnitudes, like a magnitude 5 earthquake or a magnitude 8 earthquake or whatever. But we're generally pretty sure that like in the next 100 years, the probability of a big earthquake is pretty small. It might be more of those smallish earthquakes like we've seen in the last 20 years. Those are almost certain to happen. But we're not expecting a giant one on that fault. It takes longer than that for that much stress to form on that fault. But you know what it seems like would be dang helpful? If we could predict these things, wouldn't it be darn useful to know that there'll be a magnitude 8.7 earthquake on the Richter scale in Los Angeles on December 13th, 2020? Because again, that's exactly what we need in 2020. That would be so useful. Predicting earthquakes should be really a good thing. And it is one of the great disappointments of science that we can't do it. There are no such thing as earthquake forecasts. It seems like it shouldn't be that hard. It's just rocks, which we can study, and forces, which we understand. But you need observations. And it's really hard to get 40 miles down in the lithosphere and take a measurement of how hard the rocks are and how much force is acting on them and so on. We just can't get to the places where we need to take the observations. There's no easy way to actually get measurements like that and make a prediction. Oh, I see. This rock will be breaking in the next, on this day as the forces increase on it. We just can't get there. So unfortunately, predicting earthquakes like that just does not work. That's okay, because the animals know. Every time there's an earthquake, you can find stories on the internet of my dog was banging at the door, trying to get out of the house. The birds were flying in circles. Whatever. The bugs stopped singing 2 minutes before the earthquake. The animals don't know. I'm sorry to disappoint you. Your dog is doing something crazy all the time. You just remembered it because it was right before the earthquake. The birds are always flying in strange ways. They have brains the size of a sunflower seed. They're always doing something weird. The birds, the bees, the bugs, the dogs don't know. Now, we can use historical observations to make those kind of predictions I was talking about before. Like, based on the past, we know there tends to be magnitude 6 or larger earthquake along this fault once every 10 years. That doesn't mean we think it's going to be every 10 years. We just mean the one time in every 10-year period you expect to have an earthquake like that. Those kind of predictions just based on the past are fine. And based on that, we know some places on Earth, especially the San Andreas Fault, are way overdue for earthquakes. More and more energy has been building up on them. So, we better do something about it. What would you like to do about an earthquake? Like if you could do something, you're going to make the world safer for earthquakes. What you going to do?
Probably do evacuation for it.
Ooh, you want to evacuate? Okay. All right. I like her answer a lot. Let's evacuate. Except we don't know when the earthquake is coming. It's not like a hurricane where we can watch it coming for days before, right? Or even a tornado where we might know 20, 30 minutes in advance before it comes. I like your idea of evacuating. That's going to be the right answer. But, I mean, once the ground starts shaking, it seems too late, right? Well, wait a minute. We know from our earthquake forecasting that there is a high probability there will be a magnitude 6 earthquake in Evansville in the next 10 years. Okay? That's not a particularly bad earthquake, but okay. What are we gonna do with that information? No, better yet, you are gonna go off after your graduation to a great job in Los Angeles. And I don't know if you are or not, but you know, okay, we're pretending here, right? You know there's like an 80% chance there's gonna be a magnitude 7 or larger earthquake in the next 20 years. I mean, that is something that you can find out, you know, all right, we know we're expecting a pretty big earthquake in the next 20 years. What you gonna do about that? You're gonna live your life under the table, hiding from earthquake, surrounded by your first aid kit and your fresh water and your battery-powered radio? No. The problem with forecasts like that is nobody does anything with that information, and quite rightly so. Right? I mean, what do you do with the knowledge that there's it's highly likely there'll be an earthquake in the next 20 years? Those kind of forecasts. Another one that makes me mad about that is the ones where they're forecasting the season of hurricanes. You know, you see these forecasts in the summer. This fall, there will be 8 hurricanes. What you gonna do with that? I better go board up my windows? No, I mean, even if you live in Florida, you wait till there's a storm actually coming to where you are, right? These forecasts don't do anything. There's nothing to do with them. That's not entirely true. If you are somebody in Los Angeles who is planning to build the next hospital, you use those kind of forecasts to decide, okay, then therefore we need to be this far away from the fault, and we need to have this much capacity because there's a high probability there'll be a mass casualty event in the period of time this hospital is open. But are you planning on building a hospital? I mean, that's not you and me, right? So wait a minute. I agree wholeheartedly with her answer about evacuate, or at least get someplace safe. But we don't know when to do it. I don't know when to get those kids to a safe place. What is a safe place? Aaron will tell us. I'll bet in Scouts, Aaron learned about being safe in an earthquake. Can you guess that? Damn. I would guess. Where do you go safe? If there's an earthquake, where do you go?
Isn't it like high ground?
Especially if you're near like an ocean or something, because the waves from an earthquake, the tsunami, yeah, you want to go to high ground. But let's say we're here, where should we go here? What? Where are you going? Under the desk. Aaron says to go under the desk. Drake is going to critique that answer. Is it a good idea to go under the desk during an earthquake? Why did Drake disagree? Why does Drake?
It's like steps all really opinion.
Except hit you in the head. Aaron is right. Under the desk is a good place to be. Now, Drake is not wrong. If the building collapses, the table is not going to save you. But if it's a smaller earthquake and the projector falls from the ceiling and the ductwork falls down and all the springwork from this false hanging ceiling falls down, the table will protect you, whereas it would have bonked you on the head if you were out. Okay? The table is getting under a table, or you probably heard in the doorway. The strongest part of any room is the doorway, because that's just the way the construction of it is done. I mean, that's a relatively safe place to be. If the whole building comes down, you're still out of luck. Then it's still dead. But if it's a smaller earthquake and it's just smaller things that are falling, something like the table will be fine. When I was a little kid, the same advice works for tornadoes. When I was a little kid, my parents had a pool table in the basement. And under the pool table, there was a box of toys we only got to play with when there was a storm. Okay, because then we would go down there. It was a special thing with the tornado, right? You got to go down there and there was a box of, I'm sure it was scrap toys, I don't know what it was, but it was under the pool table. And see if the lights had fallen down or the windows had broken out, the pool table would protect you. The whole house had collapsed in, it wouldn't have done anything. Okay, so I think I agree. Under the table would be a good place to be, or in the doorway. I mean, I'll call that evacuating or getting someplace safe. The problem is, by the time the ground is shaking, it's kind of too late. Right? I mean, earthquakes only last a few seconds. It's not like it's gonna be shaking and we're like, okay, children, I wouldn't want children anyway, but get under your tables, there's an earthquake. I mean, don't get me wrong, I'm not gonna say sit still, we're having an earthquake. I mean, feel free as the ground is shaking to start the, I'm gonna get to the table now. But realistically, by the time you get yourself underneath there, it's too late, right? It'll have happened. So what we really need to know is when to get under the table. And I would say, how about all the time? Let's just be under the table with our first aid kit, bottled water, and our battery-powered radio all the time. That sound good? Sure, why not? Let's live in fear. No. I mean, let's face it, safe advice will keep us safe from hurricane, tornado, earthquake, bear attack, I don't know. Zombie apocalypse, whatever we got coming our way. No, we really want to only be in the hiding place when the time is right. Who had tornado drills at their school? You, of course, everybody had tornado drills at their school. And were you good at it? When the drill happened, you guys could get there, and within a minute or two, everybody was in the tornado. Depends how big, but you could do it, right? Because tornadoes, you got a couple minutes warning. Most of the time, you have about 15 minutes warning before a tornado would strike. That's enough time to get our little kindergartners down into kindergartner space. Did you guys hear a couple years ago when we had the tornado warning and everybody got in the halls? Yeah, it took plenty of time from when the warning came to when it actually was a storm. Not that there actually was a tornado here, but there was a pretty good storm going on outside. And we had plenty of time to get there. But that's not how earthquakes work at all. What was that? Yes, that's right. I forgot some of the kids had to get pulled off the buses.
It was so bad.
Yeah, it was a bad storm. Okay.
How do we all miss one?
Okay. Fond memories of tornado warnings. Okay, so what works for the tornado warning is you have some time. What maybe as many as like 10, 15 minutes. When a hurricane is coming, you might know a week in advance. You've got time to do things like go to Lowe's and buy boards and board up your windows. And load up the car of your family photos and drive north away from the storm. Earthquakes ain't nothing like that. 2 minutes before the earthquake, you don't know anything's going on. 30 seconds before the earthquake, you don't know that anything's going on. Getting to someplace safe is really hard. But it's not impossible. You just gotta move fast. And you gotta think fast, and you need some technology to help you. Let's say that there was a big earthquake along the Wabash Valley fault. Those seismic waves that are what's going to cause the damage here in Evansville, they move fast. They move as fast as like a jet aircraft through the ground. But that fault is a good 40, 50 miles away. Those vibrations will take a minute or so to get here. Now, if we had some way to know the earthquake had happened, we would have about a minute or so to get into a safe place. A minute might be a little long. Maybe 20 seconds. So what we really need is someplace in, say, New Harmony, which is kind of halfway over that way, to have a sensor that when it measures an earthquake is happening, it sends out a radio signal ahead that would get here before the earthquake waves do. And then what we need is something in this room that would be like an alarm that goes off when it sees that signal. So if there was an earthquake right now on the Wabash Valley front, just a little bit into the Illinois side fault, and a little on the Illinois side, as the waves came past New Harmony, it would set off the alarms in here, giving us maybe 15 seconds. And in fact, this is exactly what happens in parts of the world where earthquakes are common. Up and down California, Oregon, and Washington, just like you guys have tornado warnings, they have earthquake warnings. Where all up and down Oregon and California and Washington, there are sensors that measure the very first second when an earthquake starts, It sends out a radio signal that goes to the schools, the hospitals, the office buildings. Anybody can buy a receiver, just like you can buy one of those weather alert radio things. And you move fast. This isn't like one of those fire drills, you know, where you take it kind of easy. That's gonna fly. Nope, you move. Because it could be as little as like 15 seconds before that earthquake's waves get there. But you know what? 15 seconds, if you tell little kids to get under their desk in 15 seconds, they can do it. Right? At a hospital, there's nothing you can do about all the people, the patients who are in their beds. You cannot get them anywhere in 15 seconds. But the doctors and the nurses themselves can get under a desk or something like that. And frankly, after an earthquake, you need doctors and nurses too, right? You can get those people safe. You can get people in an office building under their desk fast, and you got a lot less casualties. A lot fewer casualties. See what's going on here? So in parts of the world where earthquakes are common, like the west coast of the United States, like Japan, like Australia, these are as common as fire drills and tornado drills are here. You got to think fast. You can't wait for your teacher to say, everybody get under your desk. The moment that beeping is going, you go. And you might not get much warning. If the epicenter of the earthquake was here in Evansville, and the thing goes off, you might not have really any warning at all, right? The earthquake waves got to you about the same time that they started beeping. Well, you weren't going to be saved anyway. Right? There was no way to get the information to you. But at least the kids who live some miles away from where the earthquake epicenter is, they'll make it. That's really cool. To the best of my knowledge, there is no such system in Evansville, the Wabash fault zone. I think in the United States, only like California, Oregon, and Washington have such a thing. All right. I feel like talking about that stuff was a better day than going into seismology, the study of earthquake waves themselves, and like how we can use earthquake waves to figure out where the epicenter of the earthquake was. That's more of a Tuesday kind of thing. On Tuesday, we're gonna do it. It's a little bit technical, but that way on Thursday, we can do a lab about fighting earthquakes, and people usually like the earthquake fighting lab. You will definitely need to have your computer. Oh, that's a good point. When we do the earthquake fighting lab, we need people who have computers that are not Chromebooks to bring their not Chromebook with them. You know what I'm saying? Like if your laptop is a PC or something like that, or a Mac, because here's the deal. We need to install Google Earth Pro and EVSE notebooks, those Chromebooks won't let you install stuff. So we need it, like if your computer's a Windows computer or whatever, you'll bring it on Thursday. We'll work in groups or whatever, okay? All right, so for today, that's good enough. Let's go ahead and clean the tables and stuff and have a little nice weekend.